Good. Now that that's been all fixed. Hey, welcome back. Hopefully you guys had a pretty good spring break. So, leading off of that, welcome back. As you can see here, this is my video explaining the equilibrium Peardeck that you guys will be working on today. So, at any point in the video, if you need to slow things down, remember to take a pause and work at your own pace to make sure that things aren't going too fast. So, for slide number 1, we have this guy here. We'll call him Billy, and hopefully he has pretty good reason to be happy. So you can think of something that makes this kid right here quite ecstatic to be jumping up for joy. So, we're talking about equilibrium today. We've talked about it last week, and you might have forgotten just a bit about it. So this is why we have our recap today. Equilibrium. It's a thing that happens when our forward reaction is the same as our reverse reaction. You might have forgotten, but yes, reactions can go forward and they can also go backwards. It is possible for certain reactions, not all, but certain reactions can go forward and backwards. When that rate is the same, we call it, hey, it's at equilibrium. So, slide number 3. Going back to this idea of our reactions being reversible. And my hint to you, hey, we see one green arrow. It's not just one though. I'm seeing double. I should see 2 arrows here. Remember, reaction, usually when it goes forward, we put in 1 arrow, but if it's reversible, things can go back and forth, right? So, alright, we got my hint with 2 arrows, things going back and forth. Hopefully this hint can help you guys out in making these 4 reactions into reversible reactions. Reaction goes forward, reaction should also go backwards, and there are 2 arrows as your hint. Can't give this to you, but hopefully you guys are catching that kind of hint. Wink wink, nudge nudge. Alright. Moving on to slide number 4. Here I want you guys to draw or describe something that is dynamic. Now, you might not know what dynamic is off the top of your head, but don't worry, I'm here to explain all of that. When I say draw something or describe something that's dynamic, all I'm asking you guys to do is, hey, describe something that you see a lot of movement, a lot of change going on, right? Things that require movement, basically. But not just any movement, a lot of movement, consistent movement. For example, like a soccer game, right? Really good one at least, right? You would expect to see a lot of movement. The ball is going left and right, it's changing, it's people are making goals, right? Versus, I don't know, watching paint dry, right? Not really a lot of movement going there. That's not dynamic, right? But like a good basketball game or a good football game, right? A lot of movement would be going on. Or things like a roller coaster, right? Lots of ups, lots of downs, right? Or, right, if drawing's not your thing, right? Again, try to describe something that is. Right? And that's what I want to see on slide number 4. Moving on to slide number 5, right? I'd like you guys to draw and try to make these into closed systems. Right? You might think we don't really use open or closed systems all the time, but we actually do see uses, we just don't even realize it. So let's say we have our reaction in our beaker here, and right now all of these 3 images are an open system, right? It's an open system, meaning that things can interact with it, right? You can throw in some molecules, right? Molecules can leave, right? A lot of things can be added right now to these images, right? You can add some salt and pepper, right? You could throw water in here, right? Maybe some asbestos could drop in, right? Right now they're all open. But how can you make these into closed systems? Basically, is there any way to contain whatever we're looking at right now so nothing on the outside, nothing new is added to it? Meaning new things can't go in and things can't go out. Like for example, right, this beaker right here, you could technically plug it up, right? Put like a cork on top or like wrap it up with saran wrap, and then it would be a closed system. You might think, well, why would we want to use closed systems? Sometimes we can use it to make things go faster or make things go slower. Like perhaps if there's any way to contain this bread, if I left it out in the open, it's gonna decompose faster. But hey, maybe if I put it in a container, right, less molecules are interacting with it, therefore it's gonna decompose slower. Or if we put it in a boiling container and we close it up, right, it actually will cook faster. So try to make these into closed systems. Now, for slide number 6, it says to describe how the waves that we see in this image is an example of dynamic equilibrium. Remember, dynamic means things are moving, things are changing, right? And when you think about the waves, right, they don't ever stop, right? They're always crashing onto the shore, right? And when we talk about equilibrium, remember that's when the rate going forward is the same as the rate going back. So does the tide, is that just a one way? It's just constant, just one giant wave landing on the beach? Or does it crash and then recede, right? Forward and back. So knowing that, again, that dynamic means things are changing, things are moving, and that equilibrium, again, means things going forward is the same as the things going back. Try to explain exactly how the waves are an example of that, of dynamic equilibrium. Now we're going to move on to slide number 7. Now you're probably thinking, yeah, we're just going to copy, all right, this butterfly, but what I'd like to see here is you combine this butterfly with another animal of your choice. For example, you have half butterfly, half, I don't know, eagle, right? The wings of a butterfly and the claws of an eagle make it a beagle, I guess. It might be really cool. Right? Or, you know what? Maybe you can get creative and finish this picture in any way, sort. But I'm hoping to see some beagles out here. All right, whatever kind of chimeras you guys can create. Might be cool, might be ghastly. All right, excited to see what you guys come up with. Now, moving on to our round 2 of dynamic equilibrium. In this image, we're seeing our friend Rex. He's juggling and he's bouncing on a ball. Right? Doing a lot of juggling here. Can describe how this Rex is an example of dynamic equilibrium. Remember, dynamic means things are changing, things are moving, and equilibrium again reverts back to, all right, the forward is the same as the things going backwards. So how he has to throw up the balls up in the air and they have to come back down. Right? There's that up and down. If you threw all of them up all at once, doesn't seem like equilibrium. Right? The rate forward isn't the same as the rate back. But right now, it seems like an equal number are going up, an equal number are coming down. So knowing that these two things, you should be able to explain just how Rex juggling these balls is an example of dynamic equilibrium. Moving on to slide number 9. Ooh, traffic. Ooh, when you guys hopefully learn how to drive, you always want to be on this side right here. Hopefully not from rubbernecking. Ooh, maybe it's just that. Ooh, getting distracted by this traffic. Anywho, why is this not in equilibrium? Remember, equilibrium's forward and backward being the same. If you think of one of these sides as our forward The other side is our backwards. Do they seem equal? In case you guys didn't get the first Okay, moving on to slide number 10. Here's a challenge for you guys. It says, why might a person consider a river to be at equilibrium, but ultimately it's not? So you could argue that it is, but if you really look at the details, it's not really. Let's see if you guys can figure out this little challenge. Moving on to slide number 11. It says, what would you have to do to keep this at equilibrium? Now, what that means is, again, the rate of the water going in is the same as the rate of the water coming out. Again, it doesn't matter about the amount in here. Right? Again, it's the rate of the stuff coming in as well as the stuff coming out being equal. If we drained a giant hole, right, made this bigger, right, the water level would go down, and therefore it's not at equilibrium. If I add too much water and the water level goes up, it's also not at equilibrium. To make sure it's at equilibrium, we want to make sure that the water level stays the same. Okay, moving on to number 12. Hopefully you guys can tell me by drawing or typing one thing you've learned in today's lesson. And number 2, to draw what would you use as your superhero symbol. If you're having trouble with this part number 2, you gotta think, what's your superhero name? And kind of use that name to help design your icon. So, again, hope you guys have a pretty good day, and hope to see you guys tomorrow. See you guys later. Hope you guys have a good one. Stay safe.